All right. So if you look at this particular question, so it's about standing wave, question 6, and then it tells you that it shows positions like equilibrium and actual position. So these are in the notes actually. So you can see that it also label for you. That means the dotted lines are where the equilibrium position is at an instant at t equals to 0. This is this particular set of particles, and this is not for a progressive wave. It's actually a set of stationary sound waves. So if we look at stationary sound waves, if you want, I can actually send you a Google link. So let me maybe, or I could actually show you on, you can do a quick Google, I should have done this yesterday. So if you do stationary sound waves, you'll be able to tell that they are actually, if you look at images, I think there's one that's actually particular quite good. This is the one that I want to go into. And you can see this one, and you can see, let's see, wait for a while, because my network is also very slow. It's loading for a while. I'll let it load for a while. Hold on. Oh, I actually came in yesterday also. Okay, so you can see this. You can see that actually it's a bit different. So from this top right-hand corner, you can see this is what a stationary resultant sound wave look like. And then we are actually looking at the bottom graph, that is actually your displacement distance graph at different instants of time. So it is not a progressive wave, because I think a lot of students, perhaps they didn't read the question very carefully. They drew for me a wave profile that was actually a progressive wave. That means we are looking at actually the right one and at the bottom graph. So what you can see is the first thing we want to do is at this instant of time, interpret this. So what we have is that is the equilibrium position. So let me take out my laser pointer for a short while. So what you can see actually, this original particular dot here is supposed to be from here and has moved in this direction. Okay, so that is what it has. And then if you look at it, it's actually easier to start drawing the displacement distance graph from where from the dots at which they are still at their equilibrium position. So if you look at it, I'm actually going to start off with this. So, and then we need some convention subsequently. We are going to take right as positive according to the question. So there is only actually precisely only one graph. So those that are at the equilibrium position will be this particular dot and this particular dot, and you can actually mark it down, and this particular dot as well. So you can mark it down. This is at equilibrium position, so the displacement is 0. Equilibrium position, so displacement is 0. And equilibrium position, displacement is 0. And if you do a quick double check, you will realize that there are like the notches in between. 1, 2, 3, 4 is 4, and then the next interval is 4. So those are, they should be actually equal distance apart in terms of the notches that you make. So the next thing we want to do is draw the displacement for all the other particles. In between, it should be the ones of greater displacement. So you can actually tell whether it's positive or negative by looking at whether they are displaced to the left or they are displaced to the right. So in this case, for the first particle, it's actually at a 2 interval mark from a notch that is at equilibrium. So it should be at its largest displacement or its amplitude of oscillation, and it is actually to the right as positive. So it is to the right, so we can actually mark it down. And if you should actually try and in exams make it as accurate as possible. So I'm going to blow this up a little bit more so it's easier, and you should take a ruler perhaps and align it and make a mark at the top and make a mark at the bottom. Okay, so I'm going to remove my ruler now. Let me see, and then let's go back, and then we can now mark. So this is positive displacement, and if you put in your ruler, this will be your negative displacement, and then you use your ruler, you can actually notch off. Oh, maybe I should Okay, just tick off and notch off all the positive displacement. And then is there any more? And to interval mark, this should be a negative displacement, and then positive, and this would be a negative displacement. Okay, and then once you've notched off all these marks, then you would join with a sinusoidal graph. So this is not a semicircle, so it would look something like this. So this would be the key features that we have. All right, and this is for actually at t equals to 0. So this is t equals to 0. And according to this question, you have to label your sketch as P. So you should label your sketch as P. Okay, so make it clear and unambiguous. Now, if you look at a stationary wave, so this is at one instant of time. So for one whole cycle, the displacement versus position graph, it would actually oscillate one and come back again. Okay, so in that sense, if I look at that particular idea, then we are looking at a quarter of a period later. So I'm going to do the last part first, a quarter of a period label. Then this is at 0. And then if you go down, this is at a quarter. And so all the particles down here will actually move to this particular position. Okay, so that is the other graph. So you can therefore label this. So you should take a ruler and draw, not just freehand. So if you take your ruler and draw, and then this is actually unambiguously, this is at t equals to t over 4, and this is going to be q. And some of you actually have very good practice. You are afraid that the examiner didn't see, then you would be writing that this is at 0 displacement for all points. Okay, so it is an instantaneous graph. Okay, so at all positions or all points. Okay. So this is what we have for part 1 and part 3. Okay, so once this is done, of course you can come back, and then in the second part, the learning objective we are looking at is understanding of terminology, because I think there are certain terminologies associated with stationary wave. You need to know what is displacement antinode, and you need to know what is a displacement node. Some of you labeled multiple ones, but they just wanted one position for antinode and one position for node. So an antinode is one of maximum amplitude of vibration. And then what you would have is, therefore, you can label either one of these points. So one of these points would be either this point, this point, this point, or this point. So one of it will do. So you can just label one of it. Oops. And you can label this one, antinode. And then a node is one which is permanently at rest. So those that are permanently at rest will be actually this, and this. And therefore, you just have to do one of this. Okay, so these are all the nodes. All right, so this would be the answer, and this would be part 2. Okay, so this is explicitly testing on what is an antinode and what is a displacement node. All right, so so this is 6A. So the next part is actually quite a very classic explanation question in the formation of stationary waves, but this has a certain context. So in answering qualitative question, we still go back to this, look at the cues in the question, and this would include the keywords. Okay, so what are the keywords? What is it that you need to address? And then think of all the concepts that is required. The concepts will include actually the terminologies that you need to use, and finally link it into the context of the question. All right, so keywords, concept, and link. So what are the keywords in the question? So you're talking about stationary wave, and then you're talking about formation of stationary wave. So this would be testing in terms of the concept. So this is my keyword, stationary wave, and it's an explain. So this is also a keyword, explain. and it's about formation of stationary waves. So this is another keyword, and there are certain keywords that illustrates the particular context, and then you have a pipe that is open at both ends. So it is not a regurgitation of definition. So in questions like that, when there is a definition involved, but there is also a context involved, then what you need to do is you need to bring the context and combine it with the definition together. So we've got the keywords, and then now we can identify the context, the concept. So the context we have and the concept, the key concept that we have is about formation of stationary waves. And we know that that comes from the definition of stationary wave, and then it's about two waves moving in opposite direction. Okay, moving with and the keywords in the definition would have same speed, okay, and same amplitude. Oh, it doesn't really have to be the same amplitude, but same amplitude, but the keyword will be same speed and same frequency, and therefore the same wavelength. Okay, so keywords would be opposite direction, same speed, and all this. But there is actually another context we look at it. That means the link to the question. So if the link to the question, this is also my link to the question. So it is about a pipe that's open at both ends. So if you look at it, therefore, I now need to put in the link to the question, where are the two waves coming from? So if you look at it, there is actually a link down here where you have incident sound wave. So that gives me one source of wave that's moving down the pipe. Okay, so there is a reflection at the end. All right, and then we need to look at what is this reflection. After it reflects actually, and is it only just these two waves that is interfering with each other? Because if it can reflect off the open end on one side, it should also reflect yeah, my network is a bit unstable at times. Okay, so there is actually a context we look at, and you talk about the strings that you see. So if you notice, in the string experiment that we saw in the lab, for those who attended the lab and managed to see the lab, you will notice that the vibration is actually very small. The oscillator is very small. When it reflects, it also reflects off the ends. So again, when we have open ends, what do we need to know? We need to know that formation of pipes is about a resonance as well. So that's another context. It's a resonance phenomenon. And when they give you at open ends, there is actually a boundary condition. So there is a boundary condition, and what's the condition for it to occur? The boundary condition is such that you have displacement antinodes at both the ends. So all these needs to be put together in a particular solution. So if you look at the solution, so we are trying to do all these together. So let me switch over to the solution. You will be able to see these are the key ideas that is behind. Number one, all right, we need to talk about waves moving in opposite direction, having the same amplitude, frequency, and speed. And then we need to identify the sources of waves that are moving in opposite direction and interfering with each other. So in the context of the question, therefore, you can see that in 1 mark of the question is in the context. You first identify the waves that are interfering with each other. So we use back the terminology in the question. It talks about an incident wave. So when you send the incident wave down the pipe, it reflects off actually the other end of the pipe, and there is continuous input from the speaker and reflection of both ends of the tube. So the keyword here is actually reflection not only occurs off one end, the reflected wave of one end will actually bounce off to the other, will actually move off to the open end of the other pipe, and then they actually continually interfere with each other. So that identifies, if you look at it, the context, if you look at the context of the question or the link to the question, you realize that, okay, this identifies the sources of the waves interfering. And then we bring in the definition of the stationary waves. So this is why a stationary wave is formed, because you have waves of same amplitude, frequency, and speed traveling in opposite directions. And what they do is, for the formation, they will superpose together. All right. And lastly, we bring in the concept of, this is a resonance phenomenon. It's not every single frequency can actually have this, or every single wavelength or wave that we will have this particular formation of stationary wave in the pipeline, only when it meets the boundary condition. And what is the boundary condition? Is such that the wavelength or the frequency is such that, right, I have one more person coming in. Okay, Joria came in. Joria, can you hear me? Should be fine, correct. At any point in time, if you cannot hear me, then you tell me. All right. So what will happen is that the frequency of the wave is such that it meets that boundary condition for this particular context, is such that when you have antinodes forming at both ends, then you have this resonance frequency occurring. Okay, so it's not about just stating the equation and all that. It's about understanding and applying in context a definition and the conditions in that context. Okay, so I think key ideas, if you know the key ideas, you know the terminology, then you know what to answer. So a lot of practices is needed, especially in your tutorial as well as in your day-to-day tests. So these forms little practices. Okay, so you will notice in recent years as well, the Singapore candidates have got better and better, and the examiners are therefore looking for the proficiency in the use of terminology. So I understand this is the same for chemistry as well. So instead of using, like the tutors like to use bounce off for you to see some variation or some visualization of what is happening, but in the context of exam questions, they want specific terminology. So instead of saying bouncing off the ends of the pipe, correct? So the examiners specifically, this is a past year exam question that's taken off from if I'm not wrong, on from an A-level, a part of an A-level question. So they want to use the word things like superposed and reflected. So the use of scientific terminology is important. And then those who simply, like earlier on I say, it's not just memorizing of stationary wave, how it is formed. You need to bring it in the context. So those who re-quoted just simply the definition of stationary waveform, usually if you just re-quote a definition in a context of these kind of questions, you do not actually get any credit. So key idea, I already said, daily practice. Please try to use the keywords, and then when you look at the solutions that's being given to you, and mark up those keywords. Okay, so and I think that is very important. There is a common misconception whenever we draw sound waves in such a sense, we are actually, if you look at it, we like to draw this particular wave, correct? When we'll tell you, oh, this is the fundamental frequency. Now, what you're drawing down here is not the actual wave. It is actually a displacement versus X graph, position graph along here. So what is happening is, this is actually happening. You will get this particles that's moving, and like in the animation that I showed earlier, that is the kind of animation that you will see earlier. Okay, so it's actually a longitudinal sound wave. It's moving from left to right. So the reflection is off the ends, not the walls of the container. Okay, or else when you start talking about walls of the container, I think there's a misconception that you think that the wave is bouncing up and down. So it's not through the walls of the container. Okay, all right. So I think that's a common misconception that we see. Okay, no questions? right? So if no questions, then we move on to the next part. So nowadays, we also have more of these kind of questions. You can see that we combine this with 2024 paper 2 question 3. I think we modified it slightly because I think the last part is a bit difficult to explain. So we downgrade the question a little bit. If you're interested, you can go and look at the 2024 paper 3 question paper 2 question 3 when you buy the 10-year series, okay? Because there's a lot more concept for the original Cambridge question. But first question in this type of question is like your mini planning question. It is an experiment. You're expected to determine the wavelength of the sound and comes from the learning objective of using stationary waves to determine wavelength or speed of sound. Okay, and then the focus is on the apparatus to be used and the measurements to be taken. Now, the key concept that we have here is identifying that this is a scenario for a stationary wave. And therefore, you're not expected to put in, some people will put in pipes and then draw a string. Basically, you don't know what's happening, all right? So what you have is you have a wave that comes from speaker X, and you have a same wave because it's driven by the same signal generator. So you have wave that is coming from Y. And so you have the condition of two waves moving in opposite direction, having the same frequency, having the same amplitude, and having the same wavelength and speed, and that will form a stationary wave in between. Now, there is no condition that says that definitely an antinode is formed at speaker X or speaker Y. So that is a second misconception. There's no boundary condition here because you simply have two waves moving in opposite direction. So a stationary wave, and they even hint to you that a stationary wave is formed between the loudspeakers. So what you will have is, we don't know whether this is an antinode or not, or it could be neither. Actually, it could be somewhere in between, all right? But we do note that there will be positions of nodes and antinodes in between. So if these were antinodes, position, longitudinal sound wave, then in between, then we have nodes position. And when we have nodes position, of course, we know that distance between two antinodes will be lambda over 2. So if you cannot remember, you can draw the displacement versus position graph of the air molecules. So this is a node, this is an antinode. And sorry, this is a node, this is a node, this is a node, and then this is an antinode and antinode. And you'll be able to tell that in between two antinodes is lambda over 2, or in between two nodes are lambda over 2. Now, you can't see the sound wave. So what you need is you need something to detect this sound wave. So this is where we test you whether you know how to use the apparatus. Okay, so what apparatus is used for detecting? So if you have done your tutorial, you realize that we always have a microphone. But microphone needs something to display, correct? So your microphone is always attached to a CRO. So this is also in the learning objectives. You need to know the apparatus. So signal generator is an AC generator. And what it does, it generates voltage signals that are alternating. You can choose whether you want a sine wave or a square wave. Usually we do that, but it does not produce sound. So to produce sound, you need a speaker. So when you have a loudspeaker together with a signal generator loudspeaker, okay, it generates sound waves. But this is a sound wave generator. So if you need to detect, you need a microphone to hear, and you need to know whether it's a big amplitude or small amplitude. Microphone alone, if you don't plug into any device, there is no use for it. So the device to plug into is a CRO. What is a CRO? A CRO is just a voltmeter, but it's a special voltmeter. It's able to display the voltage signals with respect to time. So a CRO alone also doesn't work. And some of you tell me you put a CRO on oscilloscope, and then you just put it down there. It doesn't do anything. Okay, you don't tell me that you're going to move it between X and Y. So it tells me you don't quite understand the nature of the thing. So what you do is you connect your microphone, and then your CRO can be placed somewhere else. Okay, that's your CRO. And then you are going to move it along this position from X all the way to Y. And then what you do is you will look at the voltage signals, and the voltage signals that display the loudest sound will have large amplitude of voltage signals. So based on the voltage signal, you are looking at which position where you have a high intensity or high amplitude of voltage signal that is seen on the CRO. Okay, so you move it down and then you pick up all this. So between one high amplitude voltage signal to the next high amplitude voltage signal, that would be lambda over 2. Then of course, we need to also know how to measure this lambda over 2. After you mark out, okay, you could actually do this on a bench top. It doesn't really matter. You can actually use a meter ruler or a measuring tape to measure the distance between consecutive antinodes. Okay, so that's the key idea behind. So if you look at 3 marks, I think the key idea is how looking at apparatus and measurement taken. Therefore, there will be a few key points down here. Number 1, understanding that how to actually determine the positions of the nodes and antinodes. Okay, so I think that is very important. So you have the microphone connected to the CRO. CRO to actually detect, okay, the intensity of sound waves that is being, of the stationary sound wave that is being generated between X and Y. Okay, and then you need to tell us what is being displayed. So you need to say that basic idea, you just cannot tell me just the intensity. So basic idea is when the intensity is large, you actually have a large amplitude of voltage wave that's going to be displayed on the CRO. So that tells me how you are going to actually detect the positions of the nodes and the antinodes, okay? So using the microphone connected to the CRO. Then you need to tell me how are you going to measure this particular distance. So to measure the particular distance between the antinodes, after you mark them down, you're going to use a meter rule. So the 2 basic things should at least give you their 2 marks. But of course, finally, you must always link back to the question. So after collecting all this data correct, what do you want to find? You want to determine the wavelength of the sound. So if you want to determine the wavelength of the sound, then therefore you need to tell me that the distance between 2 antinodes is lambda over 2, and then so on to get the answer. So if you look at the solution, I think that's where we have where the key ideas are. So using a microphone to CRO, how are you going to detect the antinodes when the intensity, detect the points of large intensity? And how do I know that where the antinodes are? When the intensity is large, the voltage wave will display a wave of a large amplitude. Okay, at least that, or if you want to do nodes when the intensity is low, the voltage waves on the CRO will displace a wave of small amplitude. Okay, then you need to tell me, therefore, now I know where the positions of the antinodes or nodes are. Therefore, what do I do? Okay, I'm going to measure the distance. And whenever there is a quantity, you must tell me what is the instrument that is used. So distance is going to be measured using the meter ruler. Okay, and finally, I've got all this distance. What can I do with it? I can actually equate it because once I got L, I know that's the distance, and that is actually lambda over 2. I can get my lambda. Okay, so this is where the key ideas is broken down. Okay, so if you look at the learning objectives, this is a very typical setup, and there are many 10-year series questions just using this particular setup. So to be a bit more sensitive whenever you see questions with setup, to try and understand the setup rather than just apply formula. Okay, So things that were not viable, because this is not a Kunst tube setup, you don't pour sand in between and then look for the things because the sand will fly all over the place. So this is not a viable method and not what the learning objective actually wants in your syllabus, okay? If you simply just state, oh, measures microphone with CRO, the antinodes, it's not sufficient, or measure the distance between antinodes using L. How do I know they are in antinodes? Okay, so you need to have a little description on thinking about the whole process as well. Okay, there are a lot of people who also spend a lengthy amount of time to talk about how to set up. Okay, if you look at the focus, it's only a 3-mark question. It's not a full planning question. They didn't really ask you for very detailed procedures. So in going that direction, not answering the key points, that means you are also not getting all the marks. All right. So that would be that particular fact. I think, and that became a very big problem for this part for people who didn't quite understand this stationary waveform. All right, we replaced the original question was the 2 loudspeakers, but it's a bit more complex for the loudspeaker closer to the end of the year. Suppose if we do the mock papers, or if we do 2024 paper, maybe you would you can come back and look at this particular question again. So now what we are doing is we are going to replace with a microwave source, and then to make it simple, we are going to have 2 microwave sources that are identical to each other. Okay, so they are oscillating in phase with each other. So the length of the microwave emitted, so I'm giving you the wavelength is lambda. Okay, and the distance along the line is noted to be d. So I'm going to measure d from the source x. So d is distance measured from x. You may assume that the amplitudes of the microwave emitted remain constant. So what it means that as it doesn't diminish, the distance is short enough that the amplitude is going to stay constant. So this is not the displacement versus d graph of the wave, of a single wave. It is the amplitude. Okay, sketch a line to show the variation of d of the amplitude of the stationary wave that is being formed between the 2 microwave sources. Now, most common problem, people assume that you either start off with a node or an antinode. I think that's the worst thing. All right, then your entire graph is off. So the key idea here, if you look at it, if I redraw this diagram from the top, and let me just erase away all this thing. Let's assume now that all these are microwave sources. Okay, when these are microwave sources, then what happens, and then is emitting in phase, I need to determine the point of constructive interference, which is an antinode. And if you look at it, the first one would be that the path difference is 0 because they emit in phase. And that would be actually at the midpoint. Once you've got that, then you've got the wavelength, then you would know where are the positions of the other one. So midpoint, this is at d equals to 0.45 meter because d is measured from this position. This is at d equals to 0. So if you look at it, d equals to 0.45. So at d equals to 0.45 and you mark it, it should be a point of, this should be a point of, this is an antinode constructive interference. And with that, you should be able to mark up all the other points of constructive interference, all right? And then and work it out accordingly. Constructive interference is right at the center. Okay. And therefore, the next point of antinode would be, if you look at the wavelength is 0.40. So the next point of antinode would be lambda over 2. And lambda over 2 is 0.20 meter away. And if you want a node, it would be lambda over 4. That would be 0.10 meter away. So I think some of you were quite smart. You went to mark out, therefore, all the nodes instead. So these are all the nodes. This is the node, which is 0.1 meter away. And then you can mark out all the nodes here as well. And then you mark out all your points of antinode. The next thing is related to, therefore, there are numbers on the axis, and it goes all the way to 0.4. So you need to be very sensitive to this. Where is therefore, because there are only two waves, this is different from the reflection of the waves where you have multiple waves keep interfering with each other. Two waves moving in opposite direction at the points of constructive interference and at the points of destructive interference. What is the amplitude? So inherently, this question is testing you on principle of superposition. Okay, so we know at constructive interference, you have the two waves in phase that are like that. Okay, that meet. All right, so when they are in phase with each other, the net amplitude is going to be the amplitude of one plus the amplitude of the second one. And what's the amplitude? If you read off from the graph, this is 0.8. So 0.8 plus 0.8 is 1.6. So I should be marking the amplitude at 1.6. So some of you could see me counting the amplitude, and then you would consecutively continue to mark and mark and mark. Then what about destructive interference? This is where your notes are. Your net amplitude is A1 minus A2. And in this case, the waves behave the same, so it is 0. So you have 0 at that. And with this, you finish the rest of the graph. All right, so this would be for one of it. And then with that, you can actually finish with the rest of the graph and have all the markings down here. Then the next thing we want to do is to determine what is the shape. Now, this is not intensity. So it's like having a sinusoidal graph in terms of the displacement, the maximum displacement is a standing wave. Yes, so your standing wave by right has at one instant of time. So it's related to the top, all the way to the top will have, if you draw a displacement position of at that instant of time, where every one of the particle is at its amplitude of vibration, the displacement versus time graph will look something like this. But we are looking at amplitude being plotted. Amplitude is always the positive. This is why we reflect the wave upwards. So in terms of it, so you're looking at a standing wave, it's oscillating and it oscillates between these 2 points, okay, for different positions. So this particular position, okay, at this particular instant of time is one in which every particle is at its amplitude of vibration already. That's why we are trying to draw this graph. But remember, amplitude is a positive quantity. Okay, we only take the magnitude of the displacement. This is why we will reflect this part of the graph upwards and it becomes like this. And this is the shape that we have. All right. So I think of all the questions, yeah, this is the most difficult one. All right. So it would be this question. Okay. So I'm going to go on very quickly. This one I can't say much, except this is basic bookwork. And please, if you have not started compiling your list of definitions, please do so, because or else you're just throwing away 1 mark. So state the zeroth law of thermodynamics. Some tried to do it in your own words, but it's a bit different sometimes when you miss out certain words. So I'll only go through the key things that is not there. Okay, so for example, so key idea and the key picture is you have a body A and you have body B and body C. So what we are saying is that when body A is separately is important, or else it could mean that A and B are and C are all placed together, then all of them are in thermal equilibrium. This is not what Zeroth law say. Okay, or else that is another very specific condition. You can only talk about thermal equilibrium when 3 of them are all placed in thermal contact with each other. All right, so no, it's A is being separately in thermal equilibrium with body C, and then B is also separately in thermal contact with body C. Then we can say that A and B are in thermal equilibrium with each other. Now, the key words is thermal contact, if you want to use the word contact, but not in contact. Contact means physical contact. Thermal contact means there's some way in which thermal energy can be exchanged between the two bodies. All right, so they don't need to be in contact. They need to be in thermal contact. All right, so in contact, when we talk about contact, it's about this is physical contact. And no, they don't need to be in physical contact because there are three ways in which thermal energy can pass: radiation, conduction, and convection. And especially in radiation and radiation, they don't need to be physical contact as well. So be careful of using of words. Of course, there were students who didn't memorize. All right, so let's look at the next question. This one is a very typical O-level upgraded question. So this is very new. We wanted to look at how we upgrade O-level concepts and secondary 4 concepts to more systems which are a bit more complex and with less information. So you realize in this particular question, there are three objects. There is the glass beaker and there's some initial temperature. So this is the initial temperature of the glass beaker. Okay, and then there is this, so this is the mass of the glass beaker. All right, so again, some of you scribble all kinds of things without defining. Please do your definition in the question and make it clear, all right? And then so that the tutors and your examiners will know what you're looking at. So ice initially had a mass. So this is the initial mass, I'm going to use II, okay, of 15 degrees Celsius. And then finally boiling water. So this is where they give you less information because I think in O levels, we know that we're not stated otherwise, is going to be initially at 100 degrees Celsius. And then it has water of 90 grams. Okay, and then you have beaker that is shown in this figure. So then they give you specific capacity of water, specific capacity of glass, and so on and so forth, and all that. And if you look at the units, it's all in grams. Okay, so you have to be careful in terms of the conversion. All right, now they are thermally insulated and all this contents from the surroundings, so it tells me that there is no heat loss. So the exchange is all between these three bodies. So they tell you when thermal equilibrium is reached, there is both water and ice in the beaker. So here is one additional information. When you're lost for information, always read back which information I have not used. I've got a very specific technical term here. Thermal equilibrium. What information, be suspicious, it can I glean? That means there is both water and ice in the beaker. So if water and ice are at different temperatures, what will happen? If water is at a higher temperature than the ice, it will continue to melt the ice, but I've got thermal equilibrium. So this will mean that the masses of everything is constant. The masses have all stayed constant already. It's no longer melting any more ice, and that can only happen when all these are at 0 degrees Celsius. Okay, so if you look at it, you look at the glass. For it to be also in thermal equilibrium, the glass beaker, it must have gone from 28 degrees Celsius to 0 degrees Celsius. And then if you look at the water, it started at boiling water, so there's no steam involved. We are not considering steam. It went from 100 degrees Celsius to 0 degrees Celsius. So change in, but you've got ice. You've got two types of ice down here. You have ice that stayed stable, okay, as solid, and it went from minus 15 degrees Celsius all the way to 0 degrees Celsius. You also have ice that melted. And for the ice that melted, it went from minus 15 degrees Celsius to 0 degrees Celsius solid. And then it went from 0 degrees Celsius to water at 0 degrees Celsius. And this is the ice that melts during this process. And if you call this M of unknown, all right, then this one would be 90 grams minus M. So your system is set up, and who gains heat and who lost heat? If you look at this guy has lost heat. So the delta Q is going to be negative for this guy. All right, for this is for the glass. And then your delta Q for the water, is going to be negative as well because it has lost heat. And who gains heat? The delta Q for the ice, it has gained heat, okay, to do the temperature change and all that. Once you think of this, then you apply conservation of energy. So you realize now, oh, this is the step moving towards more higher level physics as well, where the problems are no longer just straightforward. Oh, I know the formulas and I just plug it in. Okay, so you need to set up the system here. So if you look at it, the whole key ideas that we want you to interpret. The final temperature is 0 degrees Celsius, and inherently you need to know that boiling point is 100 degrees Celsius. So I think that is important, but the use of thermal equilibrium is being assessed. So what do you understand by thermal equilibrium? That's why 1 mark is given to that. And some of you were not very explicit. You didn't put anywhere in your working that you knew it was 0 degrees Celsius. So we didn't know whether you were working with MC theta or MC delta theta. Okay, idea is we are not marking for answers. We are marking for train of thought in exams. And I think that coherently comes in a lot of Cambridge examiners report. Okay, please develop your answer. And then the idea of how this equation is being formed out. So if you realize it's about conservation of energy, so you explicitly, especially for a 3-mark question, you really need to tell me and very specific, how did this equation come about? Okay, logic, ideas putting in together. And what does each calculation mean? All right, so heat loss by hot water equals to heat plus heat loss by glass will be heat gain by all the ice to reach 0 degrees Celsius, and by the ice that melts to become water at 0 degrees Celsius. Okay, so all this put together and the numbers to be put appropriately. So this comes together, all right, in the correct application. Okay, so for 3-mark question, please remember to develop your ideas, or we can, and examiners will tend to try and deduct marks because they have to really think through and look through your answer. All right, so that would be the penalty. Last question, question 8 for structured question. So if you look at question 8, the first question is again a basic question, and this is a favorite question. Like I said in tests, I think almost 99% of every year's paper will have first law of thermodynamics. And this is a very super popular question. State the first law of thermodynamics, because no matter how many times we state it, there will be students who give us change. Now, writing equation doesn't give you any marks because it's about scientific writing. Okay, also. So again, definitions are unambiguous. You can use symbols to help you recall, but this is not change, it is increase. So keyword here, you will definitely get 0 if you use the word change. Is the increase in internal energy. It's not internal energy also. Okay, equals heat supplied plus work done by external force on system. So you realize the work done on system and by system becomes very important, and no ambiguity. There is only one form that we accept. Increase is about a system, not just ideal gas. So if you write ideal gas, it's also wrong. Any system will do. It is nothing more than a restatement of conservation of energy. All right. So the next thing, I think most of you were able to get this mark. Key idea, point P and C represents the gas at the same temperature. Determine the value of P. So you know that this is an ideal gas. So you use this, you can use PV equals to nRT or PV equals to nTT. Since it's at the same temperature, R is a constant, you're dealing with a fixed mass of gas, so N is constant. So you can use P1 V1 equals to P2 V2 to find the answer. So this would be for the first part. And if you work out the P1 V1 equals to P2 V2, you should be able to get the answer very easily, and you will get it to be V2 to be 750 C cubed. So most of you were able to get it. So this is an easy mark. Now, determine work done by the gas for the process. Now, work done itself, if you recall, there are two forms of work done. So you really need to know the concepts at the back of your hand. So work done, this W is work done on the system. And if you recall, we are looking at work done by the system. So work done on system is equals to negative work done by system. And here they were trying to help you. So we need to look at work done by system. When work done by system, again, the visualization is what? Your visualization is that you have the gas that is actually going to expand. All right, so you can see the gas expanding out. Okay, so it will move out and you will have this. Okay, so your basic idea is work done by gas is positive when the gas expands. So if you look at the process CA, so this is the process that we are looking at. Determine the process for process CA. Okay, this is the process. Now, and this is area under what? PV graph. So if you look at work done, work done is integral P dV. This is supposed to be on the y-axis, and this is supposed to be on the x-axis. All right. But if you look at it, this is your y-axis now, and this is your x-axis. So where's your work done? Your work done is this portion. So that is to trick students as well. So someone was very cute and wrote in my script, why switch the axis around? Because Cambridge also does that all the time. Okay, because they want to catch students who memorize without thinking. So this is the area that we want. And then, so I think some of you, I'm quite happy. You worked out the magnitude first. So you find the area. And then you deduce that from here to here, work done by the process, you can see that the volume actually decreases because it goes from a higher volume to a lower volume. So this is higher volume. And so after that, you will find the value and you give it a negative sign. Okay, in joke. So this was good. All right, so if you look back at the solution, all right, so the first thing would be to work out the area. And remember the axis, always double check the axis and do the conversion. All right, for the different units. And then finally work out the sign. Okay, so this would be for C part 1. Now, C part 2, there are error carry forward and it can kill you or not kill you. All right. So the easiest idea would be, number 1, look at work done on gas, heating and all that. And this is first law of thermodynamics. Now we switch from work done by system to work done on system. So the first thing that easiest to fill in is to transfer the value 150 here. So there is ECF here. If you had quoted me a positive value earlier on, I would expect you to fill in a negative value here. Okay. If you gave me also a positive value here, your ECF will be a deduction mark. All right. So there is an ECF mark, but it must be coherent with answer. The sign must be, and the sign and the value lah. It must be coherent with the answer in this part because we are marking concept. Okay, C part 1. All right, so in this case, the key idea is for this one, in terms of concept, is work done by system. Is related to work done on system through a negative sign. Okay, so that's the first thing. So you transfer your value over and give it a positive sign. Then the next thing we want to do is we want to fill in our first law of thermodynamics, and which is the next easier one to fill in. Okay, so actually, if you look at A and B, the first one would be apply first law of thermodynamics, increase U equals to Q plus W. This would be the easiest, and this would be positive 225. Okay, once you do that. Now, for B to C, you can't fill in at the moment, but there is one concept that we are looking at here. We are looking at Therefore, understanding B to C, if you read your question very carefully and back to here, for B to C, it may have made sense for you to tell yourself this is an isothermal process. And if it is an isothermal process and it is ideal gas, so in terms of concept, this is isothermal. So T is constant from B to C, and it is ideal gas. U is proportional to T. So change in U is proportional to change in T. So change in T is 0, change in U is 0. This is the concept to get this one. Okay, so this is the concept that is involved. And then the last one, U is a function of state. That means it depends, every single point on the graph has a unique U. All right, so if I do a process in which it comes back to exactly the same point. So if I go from A to B to B to C and so on, so if I go back to the graph, I go A to B to C to A, I come back to the same UA. So my change in U is from A all the way back to A, it is 0. So when I sum everything up, it must be 0. So this is minus 225. And once I've got that, Q is something you cannot determine from the graph. And we've got no specific heat here and all that. So we are really facing a problem of just using this particular table. So what you use is delta U equals to Q plus W. Delta U equals to Q plus W. And then, of course, Q is equals to delta U minus W. You would fill in and you would get all these values here. So in terms of marking, it's not just how many get correct. We are marking certain concepts because there are certain concepts that are used together. So the first one, this is quite unique. Idea of work done on gas equals to work done by gas, negative work done by gas. So that would be one particular concept. All right. And then based on everything on the internal energy. So if you look at internal energy, there are quite a few ideas. It would be this and this related to the internal energy. Okay. And then the last thing, so this would be the second concept that we are marking. And in the third concept that we are marking, if you realize, is this concept that is consistent. So I will check through every single value that it obeys this particular relationship. So it's marked based, the 3 marks are based on the 3 concepts. All right, and that ends the structured question. We now very quickly go on to, so this is 9:44. We are on good timing. We can now quickly go on back. Are you brain dead? I hope not. I think within 15 minutes, we should be able to end. Let me see. Quickly go back to the MCQ. Okay, so hopefully the recording turns out well. Okay, so very quickly, key ideas. I think some of you who did the past year consolidation paper question will see familiar questions popping out, because our idea is when you have done it, even if you have done it, it's okay, provided that you see the same similar type of question, you still be able to do it. All right. The worst thing you can do is we have done something similar in the tutorial and in one of a past consolidation test question. And yet, when it comes to exam condition, you've forgotten about it. Then it's maybe a really area of challenge you need to look into, because it could either mean that you didn't understand the concept. If you knew your concepts, didn't know your concepts well, or of course, it could be, I forgot how to do this type of question. Then it's something that you may want to put it to memory and try again. Okay, so I've got a parallel beam of monochromatic light laser length. So this is a very typical, oh, what happened? Okay, this is a very typical setup. I've got wavelength. So as usual, I'm looking at my keys inside my question. So I've got lambda is on a narrow slit. So this is a single slit. And then there's a slit width of B again, nano times 10 to the power minus 9, micro times 10 to the power minus 6. Be careful of it. And then it's a single slit experiment. Then I'm given a certain length L. Okay, so I've got L calculate the width of the central maximum on the screen. Now, if you recall how we tend to solve these questions, and it would look more something like that. So what is the width? The first thing to do is you visualize what kind of intensity pattern I will get. I will get a very broad central peak followed by small little minimas. So this is my intensity pattern that I will see. And what defines the width? This defines the width. Okay, what equations do I have? For equations, what we have is we've got for single slit, if you recall, oops. For single slit, what we have is we have, oh, sorry. Oops. Because my iPhone is, oh, my iPhone is also signed in. So that I know whether you can, what you're seeing actually. And yes, suddenly it went blank on me. Okay. All right. So, very sorry. Do you still see? Okay. All right. So for the single slit, this would be theta. And then we only look for positions of minima. And the first thing would be, for the first minima, we will have b sine theta equals to lambda. Then some of you will be saying, do I use small angle? Usually we don't know whether it's small angle, then we won't use small angle. Then we'll see if that's necessary to apply small angle. Okay, so for single slit in general, we don't apply until we know there's anything in the hint that requires us to do small angle. So what can we get? We have this guy, we have this. All right, so once you put in all this, you can get your theta. Okay, so you can go and work out what your theta is, and then what is the total width. Total width will need Pythagoras theorem. We have a right angled triangle here, and then this is W over 2. So we have tangent theta equals to W over 2 over L. Now, if you work out this theta, you would have gotten 40 something, I think, degrees. So remember to switch and double check that your calculator is working in the mode that you want. If you work in degree mode, you would have 46.238 degrees or something like that. Okay, so this is definitely not small angle. So we cannot use sine theta approximately tangent theta. Then once you've got this, then you, of course, your W equals to 2L tangent theta. And then you can put in this guy and then bring in this guy, and this will solve you your question 3.1 meter. Okay, and answer is 8. Okay, so a very typical single slit experiment. All right. Next question. You have security camera captures 2 LED light and so on and so forth. When you read the whole question, you realize that you're trying to distinguish the two images of the lamp in the camera. So this is what we have in a Rayleigh criterion question. So this is a Rayleigh criterion question. And because you're trying to distinguish it, that means there is a possibility that the two images cannot be distinguished. That means we are looking at a very small angular separation. So this one, the angular separation between the two images is considered very small. So we are going to have small angle approximation. Small theta approximation is going to be used, and it's usually for Rayleigh criterion question. Now, how to do this question? As usual, we do modeling. If you cannot solve the question, model it into something that you can solve. So we make it into something simple. So this is just a storyline. If you recall, it is Rayleigh criterion is a single slit experiment setup. What you have is you have two sources, and we like to put our sources like that instead. So I'm going to say this is one source, this is the other lamp. So I'm going to shift my lamp a little bit, okay? And then what we have is for Rayleigh criterion, one of the source will form a diffraction pattern, and at the point of resolution, the other source would be at this position, and it will form this. This is at the critical point of resolution. So this is, if this is source 1, this is the image for source 1, and then if source 2, this is the image for source 2. The source 2's maxima central peak overlaps with the first order minimum of source 1. That is the criteria for it to be distinguished from one another. So from that, now we can actually solve the question. So I'm going to go back to B sine theta equals to lambda. All right. So we have aperture. So this is my B times 10 to the power minus 3 because it's in per millimeter. The lengths are separated by 1.5 meter, okay, as shown. And then what's the maximum distance between the camera? So where's the camera? This is your camera. Okay, your slit is where the camera is. This is the camera aperture. All right, and then are separated, calculate this maximum distance. So we are looking at this maximum distance, and I think in your solution it uses D max. What can we find from here? We can therefore, this is where your slit is. We can work out this, my drawing not very good, so we can work out this particular theta. Because if we look at this triangle, then we can use tangent theta, opposite over adjacent, so it's 1.5 meter divided by D max. But if it is small angle, this is also approximately sine theta. So you can put your B 1.5 meter divided by D max here equals to lambda. Okay, and then with this, you can actually work out all the values. All right, so you put this in, you've got your B value, and we have the wavelength should be somewhere here. Wavelength is down here. Lambda times 10 to the power. Yeah, and that solves question 2. Okay, question 3. Question 3 is about stationary waves again. Why did we test so much? Because we didn't test so much in promotional exams. Okay, and I think we know this is a weak point. And this one is about properties of stationary wave. So that big table about energy, in phase, out of phase, and so on. So again, about visualization. So you know stationary waves, they oscillate about this point. And then they oscillate about this point. And every one of them, every particle on the wave, will all meet their maximum displacement all at the same time. All of them will go to the equilibrium position at all the same time, and then to their negative maximum displacement at all the same time. So all these particles are at their amplitude of oscillation at one instant of time, and therefore all these particles are in phase. So it's different from, this is stationary wave versus traveling waves, or progressive wave, that particular table inside your notes. All right. So all of them will be in phase. But what about if you talk about one particular segment and the next particular segment? If you're looking at one particular segment and the next particular segment, so one of it is all at positive amplitude when the other one is at half a cycle later. So this guy together with this guy, if you're comparing with this, all the particles here, these two segments are always in antiphase. And what is antiphase? Antiphase is half a cycle later, so they are 180 degrees. So these two should have been up in the first place. Okay, that would be phase difference. What about kinetic energy? We should know every one of this is oscillating in SHM. All right, so the maximum kinetic energy has to do with, therefore, what is the amplitude of vibration? At the nodes, those are the ones with maximum kinetic energy, okay? And the ones at the, if you're comparing every single particle, the one at the antinodes will all have maximum kinetic energy, my bad, okay? And the ones at the nodes, because they don't vibrate, have zero maximum kinetic energy. But here we are looking at the maximum kinetic energy of A versus B. So the amplitude of vibration for A is like that. It's going to vibrate up, down like that. So let me bring in the laser pointer. So it's going to oscillate like this, while for B is oscillating like this. Okay, so B is at the antinode, so it will have therefore a larger, this guy is at an antinode, so its amplitude is larger, bigger, and therefore it will therefore have a larger maximum kinetic energy as K8. So answer is C. All right. Okay, question 4, very quickly coming to the end. 2 more questions to go. All right, a box has dimension PQR, the box contains N molecules, so on. So this one, where does it come from? I was telling you the assumptions of ideal gas and then the derivation of PV equals to 1/3 NMC squared. This is from that part of the notes. So usually nowadays, they don't actually test you and ask you to regurgitate the whole derivation from top to bottom. They will take either components of the derivation, or like in your structured question in your tutorial, there is one where they take out certain components as well. So this is the one that takes out certain component. Here we are looking at what is the average force exerted on the shaded wall by n number of molecules, and we have a very simplified model. All the molecules are moving at speed, and this is again a past year paper. Okay, so this was from 2023, paper 1. So this time around, we want to show you that, hey, these are the questions where it comes from, and this is how Cambridge assesses. So first thing, what about average force? Why do the walls experience a force? Because the average force on the wall is through the collision of the force by the molecules, and in return, by Newton's third law, they are equal in magnitude and opposite in direction to each other. So this is Newton's third law. This is by the molecules that collide, and this is on the molecules by the wall. And what does the force on the molecules by the wall cause to the molecules? It causes it to change in momentum. And so by Newton's second law, we know it is the rate of change of momentum of all the molecules. So what we want to do is we want to estimate. So we look at the number of molecules. That will be one of the values, because it's all the molecules, but we want to look at the rate of change of momentum. And number of molecules, every one of these molecules will make a collision. So it is the momentum change per collision. Okay, but that would be over a period of time. So divided by the time, or multiplied by the frequency of the collision, because the frequency of collision tells me the number of collisions each of this molecule will make per unit time. Okay, so that will be the first thing. So let's work out the easy one. The number of molecules, of course, we know is n. Okay, these are the total number of, it looks like moles, molecules. Let me spell it out. Okay, so the number of molecules is n, so that's the easy one. Then we can look at the momentum change per collision. So this is an elastic collision. So an elastic collision, this means a before. For every one of these molecules, this is the before. And then after that, it doesn't lose any kinetic energy. So this is after it moves off. So the total change in momentum per collision is final minus initial, but it's a vector subtraction, is 2v. So, and then multiply by m. So it's 2mv. This is the change in momentum per collision of each molecule. Then what about the frequency of collision for each of the molecules? So this molecule is going to hit, impact, go, and then take some time to come back again. So it's like an oscillation. Okay, so in that case, we can associate the time between collisions. So the time between collision is therefore the distance traveled divided by the speed. So the distance traveled has to do with the horizontal distance. So the distance traveled is 2p, a different p here. This one is momentum. Okay, and this one has to do with the length p. Okay, all right. And then divided by the speed, which is v. So we've got our 2p over p. Okay. Oh no, that's time. We want frequency. Of course, we want frequency. This is the time taken for between collision. So frequency is the number of collisions. So it is 1 over delta t. So I need to flip it around. So I've got v over 2p. So with that, then your 2 will cancel, and then your p will stay, and then you have your nv squared over. So if I simplify this, this will be n m v squared over p. Okay, and answer will be A. Okay, so this is understanding the derivation and what constitutes an average force. All right, so not just memorize. Okay, so you need to know how the derivation comes about. All right, last question. So I think most of you, we actually test the same concept in the very last question. So this is an ideal gas. Here we are talking about internal energy at a particular temperature. So from the keywords in the question, what is the concept that is being tested? All right, so from the keyword, you're talking about ideal gas, internal energy, then it gives you temperature. You're looking for the relationship between internal energy and the temperature. And for an ideal gas, we know U is proportional to T. So this question is quite straightforward. 2 scenarios. The key idea is this temperature is given in Celsius. You need to convert to Kelvin. So remember, it's proportional to the thermodynamic temperature. So you have U at 0 degrees Celsius divided by U at 273 degrees Celsius equals to the thermodynamic temperature at 273 degrees Celsius over thermodynamic temperature at 0 degrees Celsius. And to convert thermodynamic temperature to degrees Celsius, so the second concept is if you've got theta, then T is theta in degrees Celsius plus 273.15. But in this question, you can see that the ratios are very nice, and then they also give you 273. That means they're not looking at, there's no decimal place behind that. I'm not looking final decimal place behind. So I will have 273 plus 273 divided by 0 plus 273, and this is equals to 2. And therefore, you would have U at 273 degrees Celsius is equals to 2 times U at degrees Celsius is this, and so the answer is B. And we are done.